okay? So higher order meaning not first order anymore, but we're going to go into mainly second order, okay? So that just means your second derivative, but this time we're doing partial derivatives, right? That's what we're working with right now. So partial derivatives. Okay, so what is this? So first of all, once you have, okay, so now we know how to calculate our f sub x and f sub y. So once you have our f sub x and f sub y, what we can do is we can take the partials with respect to each variable again. We can partial both of them, both. So what that would look like is if we take the partial with respect to x of f sub x, that's going to be equal to dx of dx, which is the same thing as the second derivative, basically, right? So this is going to be d squared f dx squared, which is f sub x sub x. Okay, so this one, this actually like goes in the opposite. Well, okay, I'll talk about that a little bit later. But this one, it doesn't matter. So basically, when you differentiate with respect to x, after you already differentiated with respect to x, we just accumulate another x here on the subscript. Okay? And the same thing for y. So if we differentiate with respect to y, the partial with respect to y already, then that's just going to equal, if we go through this process again, these are just different ways to note what we're doing. So d squared f over dy squared, that's going to be equal to f sub y sub y. Again, like I said, these are just different ways of noting what you're doing. Okay, so these, on each of these, we differentiated. We took the partial derivative with respect to the same variable twice in a row. Okay, so this was with x twice in a row with respect, and this bottom one is with respect to y twice in a row. Now let's see what goes on when we kind of switch it the second time around. So let's say we're taking the derivative with respect to y of the partial derivative of x, the first partial with respect to x. Okay, so here we're actually doing like dy of df dx. Okay, so this is a little bit different. This is d squared f dy dx. And this one, the way you notate this is you write what's closest. So you rewrite this f sub x, and then you add that little y onto the end there. Okay, so what that is, it basically works from left to right, like what's closest to the f. So this x is closest to the f, so you do that first, and then you differentiate with respect to y. Okay, so this is the first one. Okay, and then let's say we would do the opposite, so differentiate partially with respect to x, our f sub y. So this is going to be dx of df dy is equal to d squared f over dx dy, and this one, on the other hand, is f sub y, because that's what we started with, right? That was our first derivative, and then we're going to add that x onto the end, because that's what we did just now. Okay? So both of these that I've just boxed right now, when you have a combination of an x or a y, or a y and an x, or anything else, when you basically don't have the same variables there, these are called mixed derivatives, or mixed partials. Okay? So mixed partials, okay, and these are basically kind of special, right? So these are special because you have to make sure that you take note correctly, that like when you see, okay, compute the f sub y times x, so that would be the that means take the derivative of f with respect to y first, okay, because that's the closest to f, and then you do the x one, and then you do the x one, right? And then opposite for the other one, if you have f sub xy, that would be, those directions are telling you to take the partial of f with respect to x first, because that's the closest to f, right? And then you take the partial with respect to y. That's at the end there, okay? Alright, so let's practice taking the second derivatives here. So what we're going to do is calculate, and we'll say all second partials or second order partials, whatever you want to call it. Partials meaning partial derivative. Oh, hold on. Let me write that nicely. Partial derivatives. There we go. All second order partial derivatives of, and then I'll give you the function here, f of x comma y is equal to x to the fourth and then minus y times e to the x. Okay? Alright, so first of all, in order to get to the second order partial derivatives, we have to go through the first order ones, right? So let's find f sub x. So that would be the derivative with respect to x of this function. So that would be 4x cubed minus, and then that y is just a constant, right? So y times e to the x, that'll just stay there. Okay, so we have that, and then f sub y is equal to, so we have a, if we're differentiating with respect to y, the x is a constant, so the first term goes away. And then we have minus y times e to the x, so that's just a negative y times e to the x, okay? Or, let's see, wait, hold on, sorry. Back up. Okay, I can't see. So, anyway, so yes, this first one is 0. That goes away when you're differentiating with respect to y. And then we actually have, since we do have a y here, power rule, then this is going to turn into a negative e to the x, right? Because then, like, for example, if you had, like, negative 2y, then the derivative of that would be negative 2. The y goes away. So, anyways, yeah. So that would just be a negative e to the x. So this is going to be f sub y is negative e to the x. Sorry about that. And then we'll continue from here. So these are our first order partials. Okay, so first order. And now let's go on to the second order partials. So let's do the non-mixed ones first. So f sub xx is equal to the first derivative with respect, or the derivative with respect to x of that first derivative already. So that would be d dx of 4x cubed minus y times e to the x. So that's going to equal what? So we have, again, if we differentiate, we get 12x squared minus that y just stays there because it's a constant, minus y times e to the x. Okay, so this is the first one. That's our f sub xx. And then let's do the other one, the non-mixed one, f sub yy. That's going to be the partial with respect to y of our f sub y. So that would be d dy of negative e to the x. Okay, and this is going to turn out to be just a 0, right? Because we don't see any y's here, and we're already treating x as a constant, so that just goes away in the differentiation. So this is f sub y. And then now we're going to move on to our mixed partials, right? So let's do f of xy. So this one, remember, we have to be careful. So that would be differentiating with respect to x first, okay? And then our y goes on the outside, okay? So this is what we're going to have. We're going to differentiate 4x to the third minus y e to the x with respect to y. So this first term is going to go away, and the second term is going to become a negative e to the x, okay? There we go. So there's our first mixed partial, and our second one, which I will squeeze in on the bottom here, I think we can do it, is f sub yx. So that would be differentiating with respect to y first, so that's the first partial. And then we have with respect to x second. Sorry, I'm squishing this in on the bottom. I just want to get all 4 of these on the same slide. So anyways, this would be d dx of a negative e to the x, right? So then we're also going to get a negative e to the x likewise here. Okay, and this again was our second mixed partial there. Okay, so if you note, these two at the bottom, are f sub xy and f sub yx, they're both equal to negative e to the x, which shows us that, so we see on the last slide we saw that f sub yx was equal to negative e to the x, which was also equal to the same thing, negative e to the x, which was f sub xy. So what this shows us is this is actually a proof of something called Clairaut's theorem. Clairaut, I believe he was French. Clairaut's theorem, and it is called the equality of mixed partials. Okay, mixed partials. So again, mixed partials means when you take the derivative with respect to your different different variables, but yeah, that's basically it. But here it just means that like it doesn't matter which order you take them, like whether you take the derivative with respect to y first and then x, or on the right side with respect to x first and then y. You're going to end up with the same result, okay? So again, the name kind of like says it all, but it's basically just saying that the overview is that if our f sub xy and f sub yx are both continuous functions, they can't be discontinuous because then that kind of just throws a wrench into everything, but are both continuous functions on a disk D. This is just like a technical qualification here. Usually you'll see that they're all continuous. Then f of xy at sum AB is going to equal f of yx at that same point. Okay? And this is for all AB in D. That's all it's saying. So, in a more simple fashion, basically it's saying that the mixed partials are equal if they're both continuous, okay? So, another way to write this is that this is just another way to write the partial derivatives, the second order partials, okay? And this is according to Leibniz's notation, right? So, Leibniz notation, that involves the fancy D's or the normal D's, okay? So, this is Clairaut's theorem of mixed partials. All right? So that's basically it for this video. We wrapped up with Clairaut's, and we'll be doing some practice problems in the practice problems video. So I hope to talk to you there, and good luck on your homework. That is you I'm touching. I don't care about nothing, waiting for you to come and to give me that love.